let's go with it here. So give me maybe sections first. 2.2, we're at 3.3, right? At 3.4 today, if possible. All right, any questions off of these guys?
3.2, number
21, okay. Any others? All right. So that's the honesty question. How many started homework on chapter 3? No. Okay. How many got to 3.3? All right.
Oh wait, I have started chapter 3. I haven't got to 3.
Right, yeah. Okay. Cool. All right, 21. Here it is. If I can get to it. Come on. All right. Find the number, regular statute mile, and nautical mile to the nearest hundredth of a mile. That's cool. Use 4,000 miles for the radius of the Earth. Okay, let's jam. This is 21. We were talking about nautical mile. And so we have a central angle. And so there's a little picture of it like this. It has that little piece there, exaggerated, of course. And we have, is it 1 minute? Is that right? Radius of the Earth? It's 3,960, but we're going to connect these first of all. Just make it 4,000, round off figure here. And so the nautical mile, what happens here, if you go into the Navy, or if you any sea stuff that you have to go around, you're going to look at a curvature of the Earth, because that plays into the fact. If I measure the distance from here to my house, who cares about the curvature of the Earth? If I'm measuring it from here to Australia, yeah, especially if I'm taking a boat that actually needs to go like this, right? Just in case. Okay, so let's read this here. Central angle vertex center there has a measure of 1 minute. Then the arc of the surface of the Earth that is cut off by a central angle is known as a nautical mile. All right. Okay, so I guess we got to figure this out here. 80 takers first. Anything that we can think about? I don't know. Radian measurement, maybe? I think we had something called radian measurement. I think we just need to figure out what will this be in terms of just a mile, right? And so how about we have radian measurement that looks like this. Right? It's the R here, right? And it's the theta here, and it's technically labeled as T. Come on in. Let me just quickly look at this. 3.2.
Why do you want this?
That's what we did. Okay. So definition of radian measurement. It is that right there. Is that right? S over R. Theta. I'll just put theta here. So the angle measurement itself in radian measurement is S over R. So I think we have, and it's slanted there. It's kind of like falling asleep theta. There it is. Okay. So here's my formula. S over R. And that measures just this little piece right here. So I think I'm good. I just need to convert. This has to be in radian measurement, though. So, and then the radius is going to be 4,000 miles. So I think I can do this here. Multiply this by R. So R theta is equal to S. Will that work? And so the only problem is theta has to be in radian measurements. How do you convert 1 minute to radian measurement? That's no fun. I don't know. I think, isn't this true? 1/60th. 1 minute is 1/60th of a degree. I think that's true. And then what I do is I multiply this times pi, but then divide it by 180. Good there. That makes these guys drop out. And so what I really have is pi divided by, 60 times 180. Whatever that is. calculator out, so just calculate that.
It's 10,000.
800, correct. Did I talk to you guys about multiplying in our minds as opposed to a sheet of paper last time? Was it you guys? Okay.
We all were like,
Okay. Gotcha. Okay, so I'm thinking this is my theta now, and then the radius of the Earth is going to be 4,000. So I'm thinking this is what happens here. So it's 4,000 times pi divided by 10,800, and I think we're going to have something here. What is that? Mhm.
1.6, no, 1.9.
Okay, this is, notice we don't have any units except for miles here, right? And the miles came from the radius. So 1.16 miles gives us the nautical mile equivalent here. Good. Sometimes it's just 1.2. If you just need a little bit more precision, 1.16.
Does the arrow say miles?
Miles right here,
Yeah,
miles
that's
here,
one above.
miles here, chicken scratch miles. Yep. Cool. Are we good there? Let's see. Okay, let's jam. All right. Any others? Let's make this. No. That's what break is for, right? To do a whole bunch of trigonometry.
No, wireless board to break so that I can do something.
There you go. Catching up myself. Okay, let's jam then. Let's go with it. First things first is, if you jump to 3.3, something we didn't touch on is the calculator section. So if you have a calculator and you need to try it, I'm going to just show it, maybe like in 5 minutes or less here. Let's go with it here. So, dun, 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 I have this little guy. Look at that. It's a calculator. And let's see. Doesn't need batteries either. This is good.
I'm pretty sure that the computer needs batteries.
But that thing itself doesn't. Okay. Let's go with it here. So if you want to follow along, that's fine. If you just want to look, that's fine too. We have a question on 27, 3.3 number 27. It talks about using this whole concept of going around the circle and measuring your sine and cosine values right away here. So let's do it that way. Actually, it'll be easier to do it this way. Just want to show it to you, and then we'll go on here. So first things first, calculator turns on. Go to mode, and when you go to mode, instead of function right here, the fourth one down, we're going to go to something called parametric. Parametric forms, which is kind of cool. So what parametric is you have an equation for t, or equation for the x value, and another equation for the y value. You put those together, and it's a way for us to plot things. Do you guys remember in algebra, what was the number one rule of functions? Functions, something like vertical line test, some weird stuff like that. Yeah, this was a function. Parametric, So PAR. So this guy is a function, correct? For algebra 2? And then if we go like this guy, even though it's kind of fun, it's a conic section, but it's not a function. It fails the vertical line test, right? The only problem is, in our world, like, let's see, going to the moon. So when we launch, we make the Earth stationary, and if we were to fly out to the moon, the course they would take is something like this. and then we land here. Function? I don't think so. In fact, when we get to that chapter, we'll actually look at what that looks like. I think it was more like this here. I think it was, can't draw it here. I think it went like this. And it landed on the moon, and then we come back this way. That's the trajectory of us going to the moon and back. Function or no? No. It fails the vertical line test. But if I can get this guy to be the x value, and I have a function for the x value, then I get another function for the y value. I'm looking at two different functions at the same time, and I got myself two different functions. Are we good? Let's take a look at the unit circle as an intro to it. So, parametric equations, here we go. We're going to go to y equals, and notice this thing turned into an x1, and then there's a t next to it. That's cool. Let's go with cosine of t. Enter it, done. No. So when you click on this little, see it has this x, t, theta, and n. This is your variable button. Whatever mode you're in, when you click that button, that's going to be the button for that form. Sure. It's right there. It's right underneath mode. Yep, x, t, theta, and n. So theta is for polar coordinates, and n is for sequential functions. So there's your four different types. Okay, let's go with it. Sine of t is the next one. Dun, da, da, da. Close off the parenthesis just to make it look nice. And we're good. Are we good? Click and enter. That's great. Those are two functions to be looking at the same time. Sweet. Okay, I'll look at it in just a second here. Let's see. One thing I want to mention is a circle a function? According to Polymer 2, for vertical line tests. Okay. And I think let's go with graph first of all. Let's go with that. Graph. If your graph is set to -10 to +10, you're probably looking at something like that. Are we good there? Okay, and then let's go on the zoom, and we're going to zoom in, because that's too far away. I want to see what that looks like. And it has a little dot. If you see the little dot sort of flashing right in the center, right at the origin. And just click on that. And that looks like a circle, is that right? Looks like an ellipse. Yeah. Our fun calculator, the horizontal width of a calculator is wider than the vertical width. And if you're going, yeah, if you're going 2.5 this way, 2.5 this way, not good.
Nice. Very cool.
Thanks. Okay, sure.
Yeah. I know nothing. I know that I should know this. I know that I know nothing. Yeah. That's what I think. Syntax error. I just entered like those values. Six out of 9. No, I can't see it. was not that. It's something else. It's equally astounding. And it makes me feel bad about it. It makes me feel terrible about myself. Oh, yes. Yes. And at the same time, I feel like all fear with me. I was like, see. It's in a way that made me feel very. I'm just trying to imagine. And also, we did a census. But we established that Max is the Actually, that was just me. So that I could make it to 6 out of 9. It has to do with what we were talking about. And that's why I was saying that I feel like a subpar being. Well, no, I'm okay with that. No. Me neither. You're fine. Land and you makes me want to kill myself. Yeah, no, of course there's. Yeah, that's what also, it's not an invention. That's why we decided to do it.
All right, let's go with it here. Finish it up. Are we good? Try to speak with the mask here. That's no fun. Okay, let's go to Zoom. Some of you guys have did it already. So guys, to come back, so Grant, as long as you don't have a ellipse, we're going to get a circle here. And the fun part is your calculator can't do that. It's called Z-square or a Zoom square button. And so go to Zoom. Underneath the Zoom box, you're going to go to Zoom square. Number 5. And okay, it did fix it. All
so
right.
You have to
fix a calculator. All right. Now let's go one more piece here. I think we can go to window. I guess we should go to window here. Let's go to window setting here. We got the zoom fixed. Window settings. There's a few things here. So these numbers have to work out, guys. Grant, Adrian. If you're in Radian mode, right? You're going to go from 0 to 6.28 because that's 2 pi, right? And you're going the step function. If you want to make it according to the textbook, it's pi divided by 12. So you can enter it right now. So pi divided by 12. If you click on that, what the T step is your calculator calculates pi over 12 or 15 degrees. It figures it out and puts a little dot. Then it does the same thing again, puts another little dot, and then it connects them. So that's kind of what you're going with. So the Windows set, according to this, is, look at that, it's not even a nice rectangle either, right? Negative 3.78, blah, blah, blah. The Y value is at 2.5. So in order to get a square shape on your calculator, you got to go 2.5 to negative 2.5 this way, length of 5 this way, and length of 7.5 this way, right, to get that little square in there. Okay, are we good there? Are we at the window settings? Are we good?
So what is the next?
Sure. So let's go back up here. So I think most of you guys are in Radian mode.
Yeah.
Okay.
I got this stuff above. I just don't know, like my X-Men thing is different than.
Yeah, because you zoomed in, and that's just because zooming in, zooming out. As long as you have the little circle on the back end there. Okay, are we good there?
I don't see that window. Like there's a option to go to window, but it's not the same.
X is not 10.
More time on it.
No,
I just want to show you.
are you in the mode?
We got into a whole discussion calculators. Let's see. Georgia, I can do that. Just needs a little more time here. I just wanted to show you this real quick here. All right. Are we good? At least just trying to get through this here. Clicking on graph again gives you my little circle. We good? And what I want to do is I want to click on trace. That's what I want to see. And that's a little trace button. You're going to go to the left or to the right because you're increasing or decreasing. And so for number 27 on the homework, you are to the right, you're increasing the t-value. To the left, you're decreasing. So this is pi over 12 or 15 degrees. This should be 30 degrees in radian measurement. Is that true? Real quick here, son, calculator. Can you convert 30 degrees into radian measures? 30 times pi divided by 180. Is that 0.5235? Blah, blah, blah. We should have like a calculator day.
What is it?
Would that be helpful? Say again? 30 degrees times pi, then divide by 180.
What's the answer?
0.52359878. Cool. Okay, so notice this little right here. That is it right there. Notice real quick here, y is 0.5, which is 1/2. Is that right? And what should x be? If the y value is 1/2, the other one's going to be square root of 3 over 2. Let's check it real quick here. On your calculator, can you do square root of 3 divided by 2? Just want to see if it is 0.8660254. Cool. Okay. So this is kind of cool, I think. We've created a unit circle, right? With radian measurements. And we've made it with a step of every 12 degrees. I'm sorry, 15 degrees. So if we go over here, 1, 2, that should be, right there, that should be 45 degrees. Notice these guys are both the same. And I bet you that's going to be square root of 2 divided by 2 right there. And then we keep on going, and then we can eventually get to 90 degrees. Oh, this is funny. Look at that. It says negative 2.05 e to the negative 10. That's what x is, isn't it? Maybe. So this little, the 1 is correct for the y value. We good? The x value says negative 2.05 e to the negative 10. So the calculator, it's dumb. What the calculator does is it approximates it really fast. And sometimes it gets stuck. When it gets stuck, it just stops, or it exhausts its decimal possibilities. So this means actually negative 2 with 10 zeros in front of it. We good? So it's actually negative 0.0000000000205. We good? Hopefully you guys didn't count how many zeros I said. But you guys get the point though, right? It's very, very small. It is close to 0. Okay, are we good there? Just want to show you that. That's for honor students, and that's 27 on 3.3. Okay, let's jam now. I think we can do this 25 minutes or less. Less than 25 minutes or less. And then I want a little handout for you guys as well here. So let's see if we can do that all together really quick here. 3.4. And we should designate, maybe before the next test, we should designate like a calculator day, or at least go over the
Wait, so
calculator.
are we just done with 3.3?
We are done with 3.3. That was the last little piece to be had for 3.3. That's that little calculator thing. We're good there? Bam, 3.4. And let's jam quickly here. All right. It's called arc length. And area of a sector. Pretty good segment. Area of a sector. So let's do arc length first here. Arc length. Arc length. exactly what we're talking about the mile. Notice, so what we do is we think about radian measurement. Radian measurement's pretty cool. And what we say to ourselves, you know what, if let's apply this to the real world. If I have a theta and I have an r, this is still s. This is the exact same definition as I have for radian measurement, right? If I apply this to anything circular, like we just did to the world, right? I give myself this little link right here. So if I apply it to any circular thing whatsoever, a tire, right? A bottle cap, whatever it is, I have this little piece there that I can measure S if I'm trying to measure the arc length. And this is the arc length right here. It's the length that's going around something right there. A street, right? Streets are sometimes curved, right? So then you look at curvature of the street itself. Okay, perfect. So there it is. I got myself. Don't even need to change my formula. I just think about it in terms of practicality. There it is. Theta in radian measurement is R over S. Okay, if I'm trying to solve for S itself, though, S over R, thank you. If I'm trying to solve for S itself, though, I just multiply both sides by R, and there is my formula for arc length. So that gets me. All right, so let's do this here. Exercise 1. So give in a circle with angle given, angle of theta. And I've got to write all this out, and radius R. Find the arc length. Sorry, angle theta. Angle of theta and radius R. Find the arc length. I should have just said find arc length. That's easier. So here's my theta. My theta, I should say this A. My theta is 3.5. And my R value is small circle here. Theta is 3.5 and my radius is 1.5 inches. I don't know what that is. Big bottle cap maybe? I'm not sure. I'm trying to measure the outside of that bottle cap. Okay, real quick here, can you guys draw it out though first? What does it mean that I'm in radius is 3.5? Which quadrant would I be in if it's 3.5? Okay, can I skip to the next slide here? Is that okay? Tell me if I need to go back to here. If you were to draw it out, I would draw a circle like this, and I would draw from here to about right here. Right? It's all this stuff right there. That's what I'm looking for. That's the circle I'm looking at. My theta is 3.5, and my R value is 1.5. Easy. Let's turn it this around. Like this. S is equal to R theta. 1.5 times 3.5. Anybody with an answer yet? Go. I don't have the answer in front of me, so I need a second here. 5.25, anybody? Cool. Okay. Awesomeness of radian measurement. You guys ready? Radian measurement is a real number. It's just 3.5, right? There's no unit value to it. It's just 3.5. That's all it is. Right? Because the radius is in inches, we good? We have a unit value here, which is just inches. That is so cool. So there's actually a real number there, as opposed to if we had degrees in here, it would be inch degrees or something like that, right? It would not make sense to anything. But here we have ourselves a real value, a real piece there. Okay, B. How about this? All yours. And still, theta is equal to 60 degrees now, and I have radius 7 feet. All yours for that. I'm going to look up something real quickly here. Okay. Done. Answer is? Say again? I put a little trick in here for you. The angle measurement has to be in radians. Okay, or else we get this little weird degree feet thing. That sounds about right here. So let's see. We got to convert this little guy to radian measurement first, right? So before I do anything else, I'm going to have to do that. And having able to do this in your head already, you say 60 degrees, like, oh yeah, 60, 180, that's pi over 3 at this point. Because the degrees cancel, not the equal sign. The degrees cancel, the zeros are gone, so we got a really 16 over 18. 18 is going to have the 3 next to it here. The 6 will cancel. I'm left with that. Now I can plug in the formula. It just took a little bit longer. I had to do that first. So 7 feet times pi over 3. Okay. No, it's not that complicated.
Yeah, it shouldn't be.
It doesn't assume multiplication. Yeah, the TI calculators do, but not Casio. Okay, 7.3 something or other? Cool. All right, and this guy is going to be in feet. All right, a real value, a real something. That's awesome. Okay, boom. All right, we're good there. Next, let's talk about one. Oh, let's see. Let's do an application question. Let's do that, yeah. Exercise 2. So let's talk about real life here stuff. A minute hand on a clock is 4.5 centimeters long. How far does it travel in 40 minutes? All yours. So a minute hand on a clock is 4.5 centimeters long. How far does it travel in 40 minutes? I'll let you guys ponder that, think about that, draw it out if you need to. The reason why grandfather clocks really are usually about 4 feet tall. The reason for it is because that little pendulum on the bottom, it has to be a certain length. And so for it to go forward and back, right, in a second, or just this way in a single second, right, it has to be a certain amount. I already forgot how much. I think it's about 4 feet or something like that. Sorry, it has to be like 3, I forget, a little under 3 feet, I believe. So for it to swing in that single perfect second. So you have, there's a pendulum swing. Which is kind of cool. Okay, so let me draw this out. So I have a clock, minute hand is here, hour hand is here. I'm going to go from here to here. Here's my little swing right there. I'll that little clock. Eventually end up right here. So how far to the tip of that 1 minute hand travel? Guess we've got to convert to degrees, huh? So how many degrees is this? Anybody? There's like 3 different ways to do it. Any thoughts on how do we convert this to radian measurement, or maybe degrees first? That'll give you the ratio, right, of one piece to whole, which you then, and then take 360, or actually multiply by 360, right? That's cool. That's one way. Yeah, you take whatever piece you have here, 40 divided by 60, and then once you get that ratio of a whole circle, you just multiply by 360 to get what you need out of it. Right? That'll give you degrees. So then, hold on. So then, how much is it in radian measurement to go all the way around this circle? Something about 6.28. All the way around the circle would be 2 pi, right? All the way around the circle would be 2 pi. So what we have here is we have 40 minutes out of 60 minutes. Should be multiplication by a 2 pi over here, right? So zeros are gone. This is reducing down to, what is that, 8 over 6, 8 pi over 6, reduced by 2. Hey, that's cool. This is 4 pi over 3. Are we good? There's my radian measurement out of it. All right, if we did it this way, then we would have got to a degree measurement, then multiply by pi divided by 180. So I think we're good. So there it is. My angle measurement, the fact that goes across is S is equal to radius multiplied by that. Anybody with an answer to nearest 10 is fine. Nearest 10. Let's see here. 18.8. I don't have the answers either. So this is centimeters now, right? Perfect. Okay, cool. Okay. When do we do this? We do this whenever we need to measure out a curvature of something. And so spiral's a little different here, but whenever a Ferris wheel would be something like that, right? Where you measuring outside of a circle, anything that has curvature to it. Okay, that's one piece just to get you guys started here. Spent a little bit too much time on the calculator thingy, so I'm cutting this lecture just a little short here. Let's go to this one. Let's go area of a sector. All right, the drawing for it. Is this right here. Now, instead of just the outside, not like perimeter, right? Now we have ourselves the area inside there. Where do we need this? I've seen it most often in land surveying. Like not all land properties are squares or rectangles, right? Sometimes there's curvature to the land. So when a land surveyor comes out there, they have to measure that little curvature there. And so they'll stand, once they get that, then they can figure out the rest of the land, or they'll chop it up a little bit here to get that curvature. So there's that. So I'm going to just start you guys off. I think you guys can finish off the rest here. We are exercise 3. Guess what we're gonna find? Hey, there you go. You guys are bright, man. She is. So theta is equal to 2 pi over 3, and r value is 4 centimeters. I think I can do that, yeah, okay. Boom, that's going to be, we can probably slip an A as you're doing that. As you're doing that, and this out, you guys.
So say 4 centimeters.
4 centimeters, We'll deal with that in just a second here. Answer is anybody? Oh, I got a good formula, huh? Formula would be great.
Well, we're supposed to be doing.
I was gonna say.
We're all just sitting.
Sorry, guys. 1/2 r theta, r squared theta. So notice there's a little bit of an area formula in here. We don't have time to derive it, which is kind of a fun part to do. So maybe we'll do it Monday after we come back here. So A is equal to 1/2 r squared, which is 4 centimeters. We got ourselves 2 pi over 3. Anybody with that one? And then I need a second for that as well via calculator. 16 times 8, that's 8. That's 16 again. So I think exact answer would be 16 pi over 3. What's the approximation here is 10. Looks about right to me because that's 3.14 and that's 3, so they'll cancel off almost. That would be a little bit higher. So we've got ourselves centimeters and squared. Is that right? That's cool. So if we have a metal plate on our hands, right? We can actually figure out the area or a certain piece of that metal plate. All right, so there's our 2 formulas for today. And then next time we'll go into movement. How do we move stuff? And how do we, let's do one more with time here, kind of debating. As you guys are starting with that here. So theta is equal to 25 degrees. R is equal to 15 feet. So just want to convert degrees to radians. Slow down here. There you go. That might go ahead somewhere. As you guys are doing that, I have one more. This is like just for something to be. Leave your board after they freeze it. I wish I had something.
We've all thought that.
That's what it's actually do after.
That's what I think. Yeah.
Not to spoil all your break days. This is not due Monday after break. No. This is just for us to get going. It'll probably due when we take the test. So maybe like that Friday after break or something. Different homework. This is challenge problems. This is, let's see. I'm going to do this here for the honor students. Out of the 4 problems, you have to finish off 1. We good? Completely correct in everything. No. Canon students, this is, I give you some extra credit for it. That'd be fine. Just for you guys to ponder it, think about it. We good? So honor students have to finish up one of the 4. Correct, yes. So honor students, if you do more than one and get it correct, then you get extra credit. So let's go with it real quickly here. So problem number 1. Oh, we got to finish up this 2 here, huh? Sorry, let's do it for this. 25 degrees times pi over 180. Anybody got that value? So we got to convert it to radian measurement first. Whoa. No way. PowerPoint died. Thank you, Mike. Oh, went back up.
Make sure you want to scroll down. You want to pull the screen down a bit.
Okay, let's do it this way here. So 20 pi over 180 is? Anybody got that in radian measurement? 5 pi over 36 sounds about right. So angle of the sector would be 1/2. 15 feet, is that right? 15 squared? I think it was 15 feet, right? If I remember correctly? Okay. Punch that into calculator. What do you get to the nearest 10? All right. And I get a second. Grant, did you really do that? Or are you just knocking on the... Okay. Dude, okay. Prove me wrong, man. Okay. All right, so real quick here, got 35 seconds to go. Here it is. Problem number 1. It's an inner tube. I need to know how much rubber is used to manufacture a 36-inch inner tube. And the 36 inches is going to go exactly to the middle of it, the outside. I'm going to figure out that. The width of the inner tube is typically 1 millimeter in length there. So all yours there. Problem number 2, and I'll go over these problems again on Monday, right? So the Earth is spinning. We all know that. It takes 24 hours to complete 1 revolution, and at the equator, exactly at the equator, we just figure out the radius. But what happens if we want to figure out the rotation of slope itself? How fast are we spinning? And it may have to do with something we'll learn in 3.5. So we're not there yet with the spinning. Problem number 3 on the back, Cal Poly is doing an asphalt redoing problem on Deer Avenue. That is something we just covered. So the only thing you have to do is you have to figure out that angle measurement. I think you need a protractor maybe, because we needed an angle measurement. It is a curvature. And the street is some stuff. And then there's a legend on the bottom there. That's why I gave you guys a big old version of it. There's a bigger one. So there's a legend of that little thing on the bottom right-hand corner is 20 feet. So you got to figure out the 20 feet there. And I think the street, if you want to put in the street right now, the street is 18 feet across. Okay? Because if you measure it according to legend, it's 18 feet across, not quite 20. And then something we could probably do here, yeah, something about measuring the circumference of the Earth itself by Eratosthenes a long time ago. So you guys should be able to do all of them except for 2 as of right now. And have a good Monday.
So how do we turn that?
Whether you got it right or wrong?
Yeah.
You don't. You gotta just turn it in.
So we need to do one. Otherwise we don't have it.
Oh, that's good. Good job, Grace. That's good.
Thank you.
Have the best Thanksgiving. Oh, man, thank you guys. All right, and then don't forget picture day at the end of the day.
Yeah, exactly.